Good afternoon, everyone. As we continue our science seminar series, I'd like to announce that next week on February 14th, our guest speaker will be Dr. Marion McCrae from the University of Waterloo, presenting Targeting Conservation Practices to Improve Water Quality in Agricultural Landscapes. But for today, I am pleased to welcome Dr. James Paterson from Ducks Unlimited here in Manitoba as our guest speaker for today. James Paterson is a research scientist in biodiversity at the Institute for Wetland and Waterfowl Research, the science arm of Ducks Unlimited Canada. He completed his PhD at the University of Ottawa, studying population ecology of small lizards in Arizona. Prior to joining Ducks Unlimited Canada, he was a Liber Aero Fellow at Trent University, studying occupancy and extinction dynamics in reptiles and amphibians. His presentation today is titled Supporting Biodiversity Conservation with Decision Support Systems and Evaluations. Please join me in giving him a warm welcome.
Okay, thank you for the introduction and thank you all for figuring out the screen. I'm gonna talk about biodiversity conservation and the roles that science can play in helping support more efficient conservation and helping scale solutions so that we can halt and reverse biodiversity loss. I'm going to talk about the major categorical threats to biodiversity loss globally and nationally. And then the examples I'm going to give about science's role in this piece is about evaluating conservation actions, so supporting adaptive management so that we can improve the delivery of solutions, and also decision support systems that help us understand where to work and how to work to have the biggest impact with limited financial resources. So biodiversity is a word we use a lot. My favorite definition is simply the variety of life on Earth. It captures three major scales: variation within species, phenotypic and genetic, variation between species, and also variety between ecosystems. Biodiversity has inherent value that I think is worth conserving, but it also forms the basis of our entire economy. Biodiversity provides ecosystem services, which are the benefits that people derive from ecosystems. It includes climate regulation and carbon storage, providing regulation for both water quantity and quality, providing pollination services for food systems, the raw materials on which many economic activities are based, for example, lumber, genetic resources, which are sources of discovery for example, pharmaceutical and engineering new ideas, as well as providing opportunities for recreation through hiking, birding, hunting, fishing, and also pest control services by providing habitat for natural pest predators. Unfortunately, globally, biodiversity is declining rather quickly. In the most recent global report, the author stated that biodiversity is currently declining faster now than at any other time in human history. And the direct drivers of that loss were very clearly outlined in what's referred to as the Global Assessment Report on Biodiversity and Ecosystem Services. This is provided by the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services. This is the biodiversity equivalent of like the IPCC for climate. The 5 direct drivers are land and sea use change, climate change, invasive species, overexploitation, and pollution. Several of those direct drivers also interact with each other, and we expect to amplify their effects going forward. However, there's been lots of momentum globally within our society to address these threats. In December 2022, the world convened in Montreal at COP15, the 2022 UN Biodiversity Conference. And in the final hours of that conference, 196 countries, almost every nation on Earth, signed a global agreement about how we're going to move forward in addressing biodiversity loss to move towards living in harmony with nature by the year 2050. This was a huge achievement to come to the negotiations for all those countries to agree. And that global biodiversity framework that they signed has 23 targets. A lot of them are very complex and related to each other. They're very challenging. But the two that you probably have heard of before are related to targets that countries and the globe are trying to reach by 2030, including the 30 by 30 target, which is generally to conserve 30% of land, fresh water, and sea by the year 2030, and to have 30% of degraded ecosystems under effective restoration by the year 2030. So those two targets alone represent like a huge amount of progress that the world needs to make towards addressing biodiversity loss. But there's also 21 other targets related to both the sharing equitably of resources from nature, but also how society, especially private industry, is going to be required to step up to be able to finance a lot of these activities. So that's at a global stage. Canada has then, as a signing party of that framework, taken those targets and decided how we're going to apply that within our own border. So last year, Canada published our 2030 nature strategy on halting and reversing biodiversity loss in Canada. And it includes a framework for monitoring domestic progress towards those goals. So for example, the world is aiming to conserve 30% of land by 2030. Canada is also aiming to protect 30% of Canada by 2030. So each country is responsible for setting their own plan of how they're going to achieve that. Within Canada's nature strategy, it's very clear that society beyond government, including non-government organizations, have a large role to play in achieving the objectives achieving the objectives both of the global and domestic biodiversity strategy. And so the organization I work for, Ducks Unlimited Canada, we're a habitat conservation organization. We're a charity with a vision for clean water and healthy wetlands for all waterfowl, wildlife, and people. Ducks Unlimited Canada completed their first habitat project in 1938, it's in Western Manitoba. Since then, we've conserved more than 2.5 million hectares of habitat through more than 13,000 habitat projects. And so Ducks Unlimited Canada and other habitat organizations within Canada have been trying to bend the curve on biodiversity loss for a long time now. Maybe you've considered Ducks Unlimited Canada working in a different space. We might talk about it differently in terms of the benefits specifically to waterfowl, but conserving wetlands and grasslands are going to be key in achieving those broader biodiversity benefits. And so I think society already has the solutions of how we're going to conserve biodiversity. I think of them in three broad buckets: conserving what's still there, existing habitat, restoring lost and degraded habitat to compensate from that historical loss, and so that we don't end up in the same situation several decades down the road, we need to move towards societal and policy changes that will encourage us to value the true benefits that nature is providing to our society, so that we don't continue to lose habitat at a pace at which we can't keep up conserving. And so my talk isn't broadly about how we do conservation, but it's the role of science in this puzzle. And I see science playing a key role in helping fill key knowledge gaps to make these three buckets of solutions work better, work more quickly, and to be more efficient with our resources. So that includes filling knowledge gaps about where we should be doing, coming up with innovative ways to do programs in a new way, for example, in restoring habitat, but also to help implement some of those policy changes that are rolling up to help conserve habitat. So I'm going to use three examples of our work of how science plays into these different solutions. The first one I'm going to talk about is on wetland permanence classification. This is work I did with my colleagues, Lyle Boychuk, who's a manager of GIS programs for Prairie Canada, Ducks Unlimited Canada, and Lauren Bortolotti, who's a research scientist in our group. But it also included support and collaborators from local watershed districts in Manitoba, as well as local DUC conservation staff. And so to set the stage, in 2019, Manitoba amended the Water Rights Act, and they added a regulation that included a goal of no net loss and wetland benefits. That update also included streamlined processes for landowners that interact with water and wetlands. This was seen as a major win for conservation of wetlands within the province, but it included a few challenges of how it was going to roll out, and some wetlands were left vulnerable to drainage under these changes. We're talking about prairie pothole wetlands, so that's mostly in the southwestern part of Manitoba in the province. And the water rights regulation treats wetlands differently based on their classification using a system, the Stewart and Cantrell classification system that was made to identify how wetlands in these prairie systems vary with permanence. So they range from ephemeral or class 1 on the left to class 5, which have open water semi-permanent wetlands. And so they're characterized by differences in the type of vegetation associated with them. And so in the deepest part of the wetland, there's a specific vegetation community that's associated with those types. And essentially, under the new regulation, class 1 and class 2 wetlands can be drained by landowners under a streamlined registration process. So there's a simplified way that these small temporary wetlands could be drained, and then farmers could seed through those areas. Instead of going through a complicated permitting process, they could register that. Class 3 seasonal wetlands required compensation, and class 4 and 5 wetlands essentially can't be drained. The province recognized that class 1 and 2 wetlands were vulnerable to drainage under this new system, and so they invested money in the Conservation Trust to deliver a voluntary financial incentive program that pays landowners to sign an agreement for 10 years to not drain class 1 and 2 wetlands. So they receive a payment for deciding and then signing an agreement to say, okay, I will conserve these 5 basins on my land. The challenge is that in this region, there's more than 365,000 individual wetlands, and the watershed districts delivering those conservation programs need tools to be able to help identify where there are eligible wetlands to enroll in the program, and to have some tool to say, before going out and doing a field visit, do you have some idea of how many wetlands are eligible on a given parcel? And so our potential solution was to try to use both field and remote sensing data to build an online tool and then package it for the program staff that are delivering this program so they could target places that have high densities of those class 1 and 2 wetlands. And they also have a prediction of which class a wetland is before they go visit in the field to verify. The idea being that this will increase the efficiency of the program. It saves them field visits because they have some idea what's going to be on the ground before they go out and validate. So what we did was we used Sentinel-2 and Bare Earth LiDAR remotely sensed data combined with a large amount of field data to train classification models. And so because that wetland classification system is based on vegetation zones, the wet prairie, low prairie, the open water sections, we needed to be able to try to estimate how much of a given wetland basin was in those different vegetation zones. And so we built a vegetation zone classification first, and then we used a series of landscape metrics combined with the vegetation to be able to try to predict, is a wetland class 1 and 2, is it a class 3, or is it a class 4 and 5? And so we had field staff go and visit, 1,500 wetlands that were stratified throughout the province to both use as training that model, but also we held back about 560 of those wetland basins to validate the accuracy of the model after we build it. With the idea being, we then have an online tool we give to the watershed district staff that they can then identify wetlands. And so our classification model was about 75% accurate on test data, predicting to the class that they needed to, like identifying, is it class 1 or 2 and eligible to the program? 75% might be subjective. Is that good enough for this sort of program? And so this isn't an absolute classification where it's saying a wetland is or is not eligible, but it's like a targeting tool and to help give an idea before they do a field visit that validates that prediction. And so we packaged our predictions into a tool that's being used to help enroll wetlands in this program. Part of the challenge we ran into is 75% sounds pretty good. If you got a 75% on a test, okay, it's a B, almost a B plus. When you're talking about hundreds of thousands of wetlands, you're still predicting the wrong class for a lot. And so a lot of that comes down to the way the classification system works and those vegetation zones. It's meant to represent wetlands in an air quote average year, but prairie wetlands undergo very large swings in their both the amount of surface water they hold and the vegetation zones that they have based on wet dry cycles in the prairies. And so if you're using remotely sensed data from 1 year or only a few years, it really depends whether the wetland is the data that's feeding into that model is from a dry year or a wet year, and then how far outside of that range you're predicting it when we validate it later. And so this just means that there's inherent uncertainty in these systems, and there's a fair amount of subjectivity when any person goes out and looks at the vegetation in 1 year at one time and tries to assign a wetland class. But an example of how a fairly simple approach can help a policy be implemented that's enrolling wetlands to be conserved. The next example I'm going to talk about is looking at the biodiversity and waterfowl benefits from ditch plug wetland restorations. This is a restoration technique that Paterson Canada delivers across the prairie regions. So in this picture, this is a restored wetland, and in the bottom right corner, you can kind of see it almost looks like a bridge of land. That's an earthen berm. So there would have been a ditch that was dug that's draining that wetland so that a farmer could seed more of this area. And so our engineers design berms that then plug the water to hold water back. There's usually an active seed bank, and wetland plants very quickly come back once you bring water back to those systems, and then animals start using it almost immediately. So I want to acknowledge my collaborators on this project, Ash Pidorbeski and Howie Singer, who led a lot of the field work, and my colleague Matt Dyson, another research scientist in our group. So to give you the sense of scale of how much the program has been delivered and what the benefits are of understanding what sort of values these systems are providing, Paterson Canada has restored more than 3,200 ditch plug wetlands in the prairies in the last 20 years, including more than 37,600 hectares of restored wetlands. When we're looking at the small natural wetlands in the same region, that includes more than 1.1 million hectares of natural wetlands that have been conserved. So large implications of what these small wetlands are providing. So I showed you a picture of what a restored one looks like. This is a drained basin. So you can see the drained wetland been cropped through. On the right, you can see the drainage ditch, and then it almost looks like a road. That's the freshly made berm. So these are typically built in the fall when the basins are at their driest point, and then the following spring after snow melt, they'll fill up with water again. So this is a freshly made ditch where there's no recovery of water yet because we haven't had a melt. This is the following spring, it's holding water. Obviously the plants haven't come back yet. And then about a year later, there's no planting in these restorations, but you can see that it's filled with wetland vegetation and animals start using again. So we know quantitatively that the ditch plugs hold water, and we know qualitatively that wetland plants come back and ducks come back. What we wanted to do is put numbers to how many ducks come back, are they producing ducklings, how many species of other birds and amphibians start using these systems, and how fast did that recovery occur. And so broadly, we had two objectives, one looking at the duck side, one looking at the broader biodiversity benefits. And we were comparing ditch plug wetlands of various ages to small, similarly sized natural wetlands in the same system. To monitor ducks, we were using camera traps that were set to time lapse. So they are taking pictures of the open water portion of the ponds like every few minutes. And then we had a machine learning algorithm combined with human experts that were counting the number of birds and the number of ducklings. For the broader bird community and the amphibian community, we used autonomous recording units, basically microphones with a SD card that's recording in a small computer in a waterproof box. You set it to record whenever you want, and then you get thousands of minutes of audio recording of any species that's vocalizing in that system. And so I'm gonna talk mostly about the audio data and not about the camera trap duck data, since we haven't finished analyzing that. We ended up with more than 230,000 minutes of audio. That's far beyond what a human listener can process. We use a combination of human listening and machine learning to process the data. We use the BirdNet analyzer, which is a multi-species classifier created with a convoluted neural network. It's an AI algorithm. BirdNet analyzer is the multi-species classifier produced by the Cornell Lab of Ornithology. If you've ever used the app Merlin on your phone to ID bird songs, this is the classifier that's like underneath Merlin. You can run it for free on your own computer on any type of audio device. And so we use BirdNet analyzer to get confidence predictions for which species are present at which sites when. And then we used expert validation to confirm that when we said a species was at a site, it wasn't a false positive. So you can clip those specific sound clips that you think are a given species, and then you package those for an expert to validate what sound they actually are. We were interested in 3 broad questions. How many species are in restored and natural wetlands? Are the communities different in those wetland types? And how does restoration age affect the diversity of species using a site? So the first broad conclusion is that restored wetlands support lots of biodiversity. This is pooled among 90 restored wetlands and 40 natural wetlands that were sampled across 2 field years at Alberta, Saskatchewan, and Manitoba. Each wetland had a minimum separation distance. So these aren't wetlands that are all beside each other. They're all separated by large distances. You can see that we detected lots of species in both restored wetlands and natural wetlands. Now, if we start looking at the specific data points, I'm going to first look at the number of wetland bird species. So on the vertical axis, it's the number of wetland bird species we detected. On the horizontal axis, we're comparing ditch flood restored wetlands to natural wetlands. And I've pulled out that comparison by province. We expect the wetlands are fairly different between some of these regions, and the species pools are different. And so the comparison is between restored and natural within a province. Each hollow point is one individual wetland. The colored points represent the group average, and the vertical lines represent the 95% confidence interval around that mean. And so the broad pattern is that natural wetlands supported similar number of wetland bird species as natural wetlands. Lots of variation, but no systematic variation between natural and restored. Now, this is just the number of species. It's possible that different species are using natural wetlands versus restored. So we wanted to look at the community composition. The way we did this is through a multivariate technique called non-metric multidimensional scaling. And so you can think of, there's 2 axes I'm plotting here. The first scaling vector on the horizontal and the second on the vertical. Each hollow point is one site. They're colored whether they're restored or natural. And what you're looking for in this sort of plot is if the green and orange points are all clustered separately in that 2-dimensional space, it means that the compositions of those communities are fairly unique and distinct. They're different. But since they're all scattered around and overlapping, the orange and green, it indicates there's a fair amount of variation between sites in which species are present, but there's no difference in like some species being completely absent or present in one wetland type. So there's lots of variation in community, but it's not being driven by whether the wetland is a restored wetland versus natural. We also looked at the calling amphibian, the frogs and toad communities. So this is similar to the wetland bird plot, where the number of amphibian species on the vertical axis and on the horizontal axis, and comparing restored to natural for each province. The reason you get the weird clusters of points is because the communities are much smaller. So you can only have discrete number of species, and so the points are clustering on like 1, 2, or 3. And so much less variation in the amphibian community. There's not that many calling amphibians in the prairies. And they're very distinct in where those communities are. So the richest communities in southwestern Manitoba, and then elsewhere, there's often only 1 or 2 species that you typically find in a wetland. Again, we found similar number of inherent species in natural and restored wetlands. And so the final question we asked with this data was, how does the age of restoration affect the number of species using these sites? And so here on the vertical axis, I'm showing the number of wetland bird species detected at a site. On the horizontal axis, I'm showing the number of years since the restoration was completed. The colors are separating the 3 provinces in case there's a different response in one region. You'll notice that all 3 of those lines are essentially flat, horizontal. It means that there's no significant time effect on the number of species using a site. And so sites that were restored only 2 years ago had similar number of species detected as sites that were restored 15 years ago. This is good news because it means both the benefits of these sites to biodiversity are realized fairly quickly after restoration occurs. It also means that there's not strong evidence of like an aging out effect, where after 10 or 15 years, either the dams are failing or something about the vegetation community shifts so significantly that much fewer species are using them after they're so old. So these are preliminary results in that we haven't published that paper yet. But to summarize the preliminary analysis, restored wetlands supported duck pairs and broods. I didn't show you the duck data, which we haven't completed analyzing with the cameras. We've only analyzed 1 province so far. We found that restored wetlands supported as many wetland species as natural wetlands. And we didn't find a strong effect of wetland age on biodiversity in restored wetlands. So the third example that I'm going to use is on a decision support system to help us understand both spatial variation in biodiversity and also how specific programs might be benefiting or not benefiting a large number of species. We can also use this tool to look at how land cover change is affecting different groups of species. My collaborators on this project include Lauren Bortolotti and Jim DeVries. Jim's a retired research scientist in our group. Paige Cowell helped with a amount of GIS, and Ash Peter-Besky is a biologist on our team. So remember earlier in my talk, I talked about the 5 direct drivers of biodiversity loss. The first one, changes in land use. That is the single largest driver of biodiversity loss globally and also within Canada. And so to address that threat, society needs tools to estimate how biodiversity is responding to different types of land cover change. And so our approach can really be summed up in kind of two slides, these animations. The first is that landscape simplification and habitat loss reduces biodiversity. As a habitat disappears, so too will the species that relies on that specific habitat type. Conversely, habitat restoration, when done for specific habitat types that we know how in certain places in the right context, provides an opportunity for biodiversity to positively respond. You put habitat back on the landscape, species will then start using it. Really, the rest of our approach is just trying to fit the nature of these relationships and how different species respond to these changes. So our goal was to build a tool to predict biodiversity based on habitat. We did this for the entire prairies ecozone, for the 329 species of amphibians, birds, mammals, and reptiles that live in this region. And the spatial scale that we focused our prediction on is a quarter section plot of land, half mile by half mile, about 805 by 805 meters. We used finer scale land cover data within that, but we chose this scale of prediction because it is the spatial scale at which we often make management decisions. Which crop to plant in that field, which field to buy or sell, which field to deliver a restoration or conservation project on. So that was the spatial scale we chose for the output. The reason that we first did this work in the prairies is because it represents an area of high intersection, both between biodiversity. So in this map, I'm showing the density of species at risk in Canada. You can see that basically the whole outline of the Prairies ecozone lights up as an area with a high number of species at risk. It also contains more than 90% of Canada's arable land, and so it's a working landscape. It's a intersection between high biodiversity and high human footprint. And so it's a place that we need good tools to understand how can we conserve biodiversity, maybe in small natural or semi-natural habitats where we can still produce food to feed our country, and so our economy keeps running. And so our approach was to combine observations of species with information on both habitat and climate. Although we are most interested in predicting the effects of habitat on species, we know that climate affects both the range limits of species, but also the probability of a species occurring in different places within their range based on climate. We built species distribution models for all of those species. And then when you stack the outputs of those models, you can get a sense of spatial variation in biodiversity and also an understanding of how that community is responding to the input variables, such as the amount of habitat. We used basically the best available data we had, including more than 1.2 million observations of species that included public data sources that you're probably familiar with, like iNaturalist, GBIF, eBird, but also through data sharing agreements with the conservation data centers, which are the provincial agencies tracking rare and endangered species. We used Agriculture and Agri-Food Canada's semi-decadal land use, their land use time series product for land cover. And then we used WorldClim to model how variation in climate affects species. If you're familiar with species distribution models, you know that typically the kind of typical version of an SDM includes climatic variables, so the bioclimatic variables that summarize variation in precipitation and temperature through space. We included those, but our focus was also on including ecologically relevant habitat variables, such as the amount of habitat within a field. So like the amount of wetland within one field, how that affects the probability of a species occurring there, as well as patch size effects. We know that several species require not just a certain amount of habitat, but a continuous patch. This is especially true of, for example, native grassland specialists. And then we tested and validated our models through several different ways. One is through both iterating, fitting the model with different folds, spatial folds of the data, so we could estimate uncertainty in our predictions. We use the classic cross-validation approach where we're holding back observations to then test how well the model performs using similar data types. But then we also tested the accuracy of the models using independent data. So the last section I told you about some of the recording data we have of species at given sites in the field. Both through that study and several other studies where we're collecting species observation data, we looked at how well the tool predicts which species we observe in a field. And so using that independent data, we found, for example, really strong correlation between what our tool predicted the number of wetland species would occur there versus the number of wetland species we recorded on those ARUs. So when we roll up that work, we can get, excuse me, spatial predictions of how biodiversity varies through space in terms of the number of species. To illustrate what this might look like on the ground, if you're making, for example, conservation decisions or trying to report on the benefit of a conservation program, this is an area in Western Manitoba where I'm showing the tool's prediction on 2 fields that are separated by less than 2 kilometers. And so on the left, you can see a field that has some forest patch, a number of remaining wetlands, some native grass connected on the quarter beside it. The tool predicts that habitat supports 136 species. Just a few fields away, there's a site that has almost no remaining natural wetland, no forest cover, it's mostly annual crop. The tool predicts supports 71 species. And so even within a very small amount of space, we get very large differences in the number of species we're predicting occur at a site. And so this ability to predict variation in the number of species is useful from a conservation planning perspective to say, we're going to deliver a program here that might benefit the most species or might benefit this type of species that you're targeting. We can also use these predictions to sort of look back at programs and say, how many species are really benefiting from a given type of program? And so in this landscape, a lot of conservation work focuses on small patches. For example, conservation easements are a voluntary program where a landowner receives a payment for negotiating, conserving a certain part of their land. For example, the wetlands within their fields or a small amount of native grasslands within their land. And so we were interested in, well, these small patches, how many species are really benefiting them compared to just, a random area within a small distance of that. And so we took sites where there are conservation easements and compared them to unprotected sites nearby to answer, do they have more natural habitat and how many species do we predict are there? So on the vertical axis, I'm showing the predicted number of species. On the horizontal axis, I'm comparing conservation easement sites to sites with no protection. And then each hollow dot represents one site. The gray lines are connecting paired sites because the design we took was to pair an unprotected site to an easement within the same area because they'll support similar types and numbers of species. So if you compare a site that's far away, a whole bunch of those species just won't geographically occur there. So we're constraining our comparison to a small area. And so using this approach, again, lots of variation, but conservation easement sites were predicted to support 39% more species than unprotected sites. And so this is pretty good evidence that a program that protects small patches of habitat is having a relatively large benefit on conserving species in these working landscapes. We also used our tool to ask some questions about what are the major drivers of biodiversity loss that are related to land cover, and how can delivering small amounts of natural habitat protected in that landscape benefit species. So we simulated land cover change for the major agricultural land cover conversions that we expect. So on this plot, I'm showing the results of one of those simulations where on the vertical axis, I'm showing species richness as a proportion of maximum. And on the horizontal axis, I'm showing variation in the amount of that field that's planted to annual cropland. And so on the far left, it would be, not a crop field. It would be a mix of wetlands, native grass, and a small amount of forest. And as you slide to the right, you're planting more and more of that field into an annual cropland, and then seeing how the number of species predicted to be supported in that area changes. So this was the single greatest link between land cover change and biodiversity that we found. And then we can ask questions like, if we conserve a small amount of that field, let's say 20%, how many species would you still have compared to originally? And so in this scenario, conserving 20% of natural habitats conserves an average of 27% of the original species that occurred in this area. Now, if we compare that to a different type of agricultural land use, for example, tame pasture or haylands, the pattern is very different. So I'm showing the same plot, but now on the horizontal axis, it's the proportion of the field that's in tame grass or perennial cover. In this scenario, conserving just 20% of a field of this type can still support 74% of the original species that were predicted to be there. So in this way, you can see the relative difference in terms of conserving a small amount of natural habitat on a tame grass field. You can still support most of the original species that were there. So these biodiversity estimates with species distribution models can be useful for generating spatial predictions in biodiversity, which is useful for conservation planning. They can help us estimate the benefits of different conservation actions. For example, the example I showed you with conservation easements. They can also help us identify what are the major drivers of variation in biodiversity in this system. So I kind of ran through my 3 examples. If I had to leave you with a take-home message, the 3 that I think are most important, first is that biodiversity is declining, but we already know what works in terms of conserving biodiversity. We just have to accelerate the pace at which we deliver it. And then we can help use science to help fine tune how those programs and solutions are developed. Science can really help deliver evaluation studies to measure the benefits and support program adaptation, and also build decision support systems so that we know we're working in the right places and doing the right work to make sure we're being efficient with the limited amount of resources we have for conservation. Thank you very much for listening, and I'd be happy to take any questions.